Alright, now we're back in section 7.4 on vectors. This is kind of a long section of material, so it's going to be broken up into a few videos. In the first part of the section, in the first video, we talked about what a vector was, about how a vector was described by magnitude and by direction, and how we could represent a vector on a plane by drawing a line segment with a dot at what we call the initial point, and an arrow at the other end point called to give the direction. This is called the terminal point. And we also talked about how we could find the magnitude of a vector. We did an example where we had some ordered pairs that showed the initial and terminal points, and then we were able to use those ordered pairs and either create 3, 4, 5 right triangles, or we could use the distance formula. Either way. Now, if we wanted to go ahead and work with vectors, one of the things that we have to do is we have to consider the possibility of two vectors at the same time, perhaps acting upon a body in which we would want to add the vectors. Now, what I mean by that is if you consider yourself, let's say, jogging down a street, you have direction and your speed of your jogging is your magnitude, so your jogging actually could be represented by a vector. And at the same time, let's say there's a wind blowing from maybe behind you, but a little bit to maybe your right side. Well, the wind blowing would probably speed you along, and of course the wind blowing from maybe one of the sides might make how you run, you might have to put a little bit more emphasis to stay straight by maybe running a little stronger against that side so that you're not going to the left, but you're going straight as you jog. So what we want to be able to do is we want to be able to add vectors. Now, to add vectors geometrically, we have two different methods. And what we're going to see in the next video is how we can do this a little bit more algebraically. But as far as geometrically, we're going to use one of two methods. One method is called the parallelogram method because we construct a parallelogram, and the other one is the consecutive method because we typically draw our vectors tip to tail. Now, remember, vectors are equal if they have the same magnitude and they have the same direction. That was one of the things we talked about also in the last video. So for me to take these two vectors here, vector u and vector v, and to add them, I'm going to have to be able to construct these two vectors. So one of the things I'm going to do is I'm going to measure its magnitude there. It looks like 8 inches this way, and it's kind of angled off. Now notice here, it's asking me to add u plus v. As it turns out, v plus u gives you the same thing. Vector addition is commutative. So I'm going to move this stuff out of the side here, and I am going to do my very best to construct, well, let's see if I can do it. I'll have to bring it down a little bit. To construct a vector, now if I go to 36, that would be 28 right here. That's in the same direction. Now I had to kind of eyeball that. I could have gotten a protractor out and measured to get the angle, or easier yet would be to do this with graph paper, and so you could get a better idea counting squares. But this is my vector u right here. Nope, actually, I'll tell you what, let me move that over just a hair. I didn't give myself enough room because I forgot about how far v goes to the left. So let's try this again. I'll bring it down a little bit, trying to get the measure right. Okay, so this, best I can do with, under the circumstances here, or one of the, as well as I could do here, this is vector u right here, same direction, same size, and let's figure out that this is, looks like about 12 inches, and it's going in this direction here, so I'm going to do my best here to draw this. Now, when you do the parallelogram method, this is the first method I'm doing, we want the, what I call the tails, the initial points to be the same spot. So I'm going to try to get my angle here, to get my direction, and then I'm going to count, see, this would be, right there we go. and this would be vector v. Now notice that I've drawn these here. I'm going to put this up here because I might need some space. Let's find vector u plus vector v. I'm going to use the parallelogram method, which means I already have 3 of the vertices of a parallelogram. And so what I need to do is I need to figure out where my 4th vertex is. So I'm going to try my best to keep the same direction and construct this parallelogram. Now I'm eyeballing it, so bear with me here. But it looks like it would be about like this. And I'll make this dotted so you can see that this is not a vector but part of my work. And then this way here, hopefully, there we go, let's see if we got this. Okay, we kind of missed it there. We'll have to maybe make that a little bit longer. Kind of missed it there. But I have, using what little talent I have here for drawing, I have tried to construct a parallelogram that has these 2 vectors as 2 of the sides, and I have created the other 2 sides finding the 4th vertex. The sum of the 2 vectors goes from where the initial points meet to this 4th vertex. So now I'll use a different color pen here so to kind of try to bring that out a little bit. Not quite straight up, but pretty close. And the initial point of the sum of what this is adding up to, which we call the resultant, the initial point is the same as the initial point of the other 2 vectors. The terminal point is at that 4th vertex, so I'll put the arrow there. And this would be my sum. This is vector u plus vector v. And again, we call that the resultant vector. Now that's the parallelogram method. I like using the parallelogram method when I'm adding 2 vectors, especially if the vectors are describing forces, which vectors have a tendency to do. So the other method, the consecutive method, I'm going to try to put it right here next to it. And what we do here is we, again, I have to draw the original vector u here, so I'm going to try to approximate this best I can. As I remember, it was, I think it was 8. 1, 2, 6, 7, 8. So, no, wrong color pen. Okay. Well, I don't know if I get that one right. Let's see, did I get it right? I did not. My pen didn't mark properly. There we go. Well, that's not much better. Let's try it again. The better you draw these, the more likely it is that your answer will be in the ballpark. Alright, so from 28 down to here, I think it's slipped. Here's vector u. Okay. Now, in the consecutive method, rather than putting vector v so that the terminal point is at the initial point is at the initial point of the first vector, you put the initial point at the terminal point of the first vector. So I'm trying to approximate this. Let's see if I can get this direction about right. That looks pretty close from what I can tell. So there's vector v. Okay, and that's all you have to draw as far as finding the resultant vector, because the resultant vector, and you may be able to see this coming, the resultant vector goes from the initial point of the first vector that's being added to the terminal point of the second vector that's being added. So it goes from here to here. If I can draw this decent. Well, I think it's slid a little. And then this would be vector u plus vector v. Now, I look at these, and even though I kind of took my time and made mistakes and tried my best to make these reasonably good sketches, they don't look too bad. Don't they look like if you look at them here, don't they look like they're the same size vector and in the same direction? And they should be, because you're adding the same two vectors. The answer should be the same. It's unique. You don't add two vectors, get one answer, add them again, and get a different answer. So that would be how you do this geometrically. Now again, I like this method when I'm just adding two vectors, but when you're adding more than two vectors, the consecutive method comes in handy, because if you, let's say you're adding three vectors, using this method, you'd have to add two, get the result, and then do the parallelogram method again with the result and then the third vector. But here, if I have three vectors, and let's say the other vector maybe kind of goes this way, I just tip the tail it this way, and it goes from the initial to the terminal. So you can add multiple vectors a little bit more conveniently using the consecutive method, or sometimes I just call it the tip the tail method. Alright, that's done. Now, you should be able to add vectors geometrically, and as it turns out, we can not only can we add vectors, but we can take multiples of vectors, and we can also subtract vectors. That's what I'm going to show you here. It says if a vector v is multiplied by a real number, which I call k here, the magnitude of k times my vector, now notice there's no arrow over the k, that's a constant, is the absolute value, notice two lines here because the absolute value of a number just has the single bars on each side, times the absolute, or the magnitude of vector v. Notice the double bars there on both sides. So this is a number, this is a vector here. But when you take the magnitude of a vector, this becomes a number. So you have a number times a number, it's going to give you the size of the vector, the magnitude of the vector. The direction of a multiple of a vector v here is in the same direction as v if k is positive, but it's in the opposite direction of v if k is negative. And we call k a scalar. You remember I was trying in the first video, I was trying to distinguish between a scalar quantity and a vector quantity. Remember, a vector quantity had both magnitude and it had direction. A scalar just had magnitude here, absolute value. So, if we have k times v, it's called a scalar multiple of vector v. These are not negatives, these are just little marks here to indicate three statements. And the zero vector, and there is such a thing as the zero vector, and we denote it with a zero, with a vector symbol above it, has magnitude of 0, and is assigned no direction. Well, graphically or geometrically, if it has magnitude of 0, it'd just be a point. The zero vector would just represent a point. And of course, a point doesn't designate direction. Now, I have vector v that I've drawn here. I believe it's the same vector that I have here. I'd have to double check. But if I take vector v and I multiply it by positive 2, I get a vector that's in the same direction but just double the magnitude or double the length, and that's what I've tried to show here. This vector times 2, the scalar 2, gives me 2v. Notice the same direction. We said try to draw it so that it looks like the same direction, and double the size, double the magnitude. Negative 2v, if I multiply this by negative 2, well, the magnitude doubles, but the direction's the exact opposite. And notice here, the arrow's down at the bottom, indicating that it's going in the exact opposite direction. And then I took this vector and I multiplied it by negative 1/2. Well, the negative 1/2, the negative puts it in the opposite direction. The half brings the magnitude in 1/2 its size. And notice here, from here to here, also going in the opposite direction because of the negative. So you can draw geometrically vectors and scalar multiples of vectors by using a ruler and being very careful and doing some measuring. Don't just freehand it. I get students that just freehand these things because they don't want to bother finding a ruler. Alright, now over to here. Because we can multiply by a scalar, by a real number, if we multiply by negative 1, we get what we call the opposite of vector v, which is negative 1v. That means it has the same magnitude, but it's in the exact opposite direction. And because we have the opposite, we can now subtract vectors, because subtraction, just like with real numbers, is the same as adding the opposite. Notice, subtraction here is the same as adding the opposite. And remember, the opposite means you're multiplying it by the scalar of negative 1. So I'm going to use these two guys again, and I'm going to subtract here using vector u minus vector v. Now again, based on this, this tells me that this is vector u plus -1 times vector v. So first one first is vector u, which I think I measured was 8. Yeah, it was 8 inches. So I'm going to approximate it best I can from all the way over here. Let's see if I can do this. There we go. And so now I have 8 would go to 22. There we go. There is vector u. Now, vector v, I believe, was 12. Yep. And it was kind of going up and to the right. Well, I still want that. I want that slant. But I'm going to go in the opposite direction. And I am using the parallelogram method. If you haven't already noticed this, this is the opposite of vector v. Notice tail to tail, or initial point to initial point. And then from here, I have to complete my parallelogram best I can. There we go. And I draw in. I'll use a different color vector. Marker. And vectors on the mine. It goes from the initial point to this fourth vertex of my parallelogram that I've drawn. And this would be vector u minus vector v. You can use the consecutive method as well, because as long as you're adding vectors, you can use either method, and you're adding the opposite, so you're adding two vectors. It's just that it's the opposite of the one. And notice here, look at my answer here when I add them. Look at my answer over here when I subtract them. And I'm not really looking like they're related in any way, but this is how you add and subtract vectors. Now we're going to do some more with this, but we're going to try to do more of an algebraic approach here in the next videos.